Welcome, my name is Lesia, and today I would like to talk about existence of simpler machine learning models. It is expensive to optimize for sparsity or interpretability. For example, this is a 4-line simple model produced by an algorithm called Corals based on ProPublica dataset. And this algorithm produces rule list, which is a one-sided decision tree, and in order to do that, it searches an enormous space of decision trees with smart bounding techniques. In fact, it is proven that it is NP-complete to construct an optimal binary decision tree. So in order to find good models, it is actually really hard to do so. And an important question arises. Is there an easy way to check that the search for accurate and simple models will be fruitful before we actually spend so much time and computer resources and go and find it? And you will see in this talk that the answer is yes, and it lies in the understanding of the Rashomon sets. So let's look at the simple illustration, where on the x-axis we have a hypothesis space, and on the y-axis we have empirical risk. Then yellow bar will depict our hypothesis space and all functions f that lie within it, and black curve will depict our empirical risk. So then let's also say that user is given us some parameter theta, and this parameter basically signifies how much user is willing to sacrifice for the interpretability or sparsity. It can be 1% or 0.5% of the loss. So this parameter, we will call it Rashomon parameter, and it defines a threshold. And all models that lie below this threshold will actually belong to the Rashomon set. Meaning that Rashomon set is a set of models that all perform approximately the same, approximately well. And as you see, it can contain models from multiple local minima or from one specific local minimum. More formally, Rashomon set is all functions f such that the empirical risk of this function f is less than equal than empirical risk of the best model of the empirical risk minimizer plus that Rashomon parameter theta. And by its definition, the Rashomon set is a property of hypothesis space, of a data set, of a loss function that we choose, and for the Rashomon parameter. There is a nice question also, how can we somehow quantify like how large or small the Rashomon set is? And to do that, we will introduce Rashomon ratio. So Rashomon ratio is a ratio of the size of hypothesis of the Rashomon set to the size of the hypothesis space. Meaning that for example, if our hypothesis space is discrete, that would be cardinality of the Rashomon set divided by the cardinality of the hypothesis space. As you recall, Rashomon set dependent on hypothesis space, on the loss function, on Rashomon parameter, and on data set. Thus, Rashomon ratio is a way of a measure how complex or simple our learning problem is. So in fact, it is a simplicity measure of a learning problem. The larger the Rashomon ratio, the easier it is to find similar models because the most good models the Rashomon set contains. As a simplicity measure, Rashomon ratio is different from other known complexity measures. So it is different from VC dimension because VC dimension is data independent and Rashomon set is. It is different from geometric margins because geometric margins, they are measured with respect to one model. Also, we shown that there are cases when you can have a small minimum margin and large Rashomon set. It is different than Rademacher complexity because Rashomon sets do not measure changes in targets. And also we constructed an example where you can have, in fact, the same local empirical Rademacher complexity and different Rashomon ratios. And finally, it is different from algorithmic stability. Again, Rashomon ratio do not measure the robustness with respect to changes in data, but also we've shown that in case of ridge regression, Rashomon ratio will stay the same when algorithmic hypothesis stability will actually changes. Before we dive into more important results, I would like also to discuss with you two more concepts. One of those is true Rashomon set. So true Rashomon set is very similar to Rashomon sets or empirical Rashomon sets that we just discussed. The difference is that instead of looking at an empirical risk, we actually look at the true risk. So in this case, the true risk is depicted as black curve, and we are looking at all models F, such that true risk of F is less than equals and true risk of optimal model F star plus, and gamma is again the Rashomon parameter, but we just use a different notation to differentiate true and empirical parameter. Another concept would be that we will actually consider two spaces. So we have a hypothesis space that we will denote F2, but also we have a simpler hypothesis space that lies within F2, and it will denote it F1. So then, if the true Rashomon set is large enough to contain one simple model from F1, and we do not need to know which that model is, we just need to know that it contains it, then the empirical risk of the empirical risk minimizer of F1 actually enjoys these good generalization guarantees because it is close to the true risk of the model or optimal model of F2. Let's also show it more formally. So we will have a bounded loss, and we will again say that the Rashomon set is large enough to contain at least one model from F1. Then for any epsilon greater than 0 with probability 1 minus epsilon, following bound holds. This bounds the empirical risk minimizer of F1 with true risk of F2 star with the optimal model from F2. And then the lower bound will depend on the complexity of F1, not F2 as in majority statistical non-series bounds, and the upper bound will actually depend on the Rashomon parameter. So this tells us if the Rashomon set large enough, actually we can go ahead and optimize F1 because the empirical risk minimizer of F1, that models that we will find, will have good generalization guarantees. Let me also introduce an example of how we can use this theorem as well. So let's say that F1 is a random sample of functions from F2, and we are sampling without replacement. So that means if F1 contains 10,000 models, then the bound that we just saw will hold with probability 99% if the Rashomon ratio is at least 0.05%. So that's more the Rashomon set should be in order for us to get that bound to hold and search for 10K models. Okay, let me also give you another example, because we just talked about true Rashomon sets, and the condition by which we need to check if it contains one simple model, we cannot check it. So let's consider empirical Rashomon sets. Let's consider again empirical risk, and let's make two assumptions. One would be that our loss is smooth, so we have K-Lipschitz loss. And another one is that we have good approximation guarantees between our spaces, meaning that for every model F from F2, there exists a model G from F1 such that they are delta close. In this case, the Rashomon set, the empirical Rashomon set, contains at least packing number of simple models. And the larger Rashomon set is, the more simpler models it will contain. And all these simpler models will again enjoy good generalization guarantees because their bounds will depend on complexity of F1 and not F2. And just to remind you, the packing number is the number of disjoint balls that can be fit into the space. Okay, so going back to our original question, now we know that the answer is actually if the Rashomon set is large. What we don't know is how to measure, how to understand if the Rashomon set is large, which is another difficult problem by itself. But we notice a very interesting things that happen in practice. So what we did, we considered 5 different machine learning algorithms. So we have logistic regression, CART, random forest, gradient boosted trees, and SVM with RBF kernel. And to measure the Rashomon ratio, we use space of decision trees of depth 7. They're complicated enough to model different data sets, yet they are understandable and simple enough for us to sample and try to compute Rashomon ratio. We did this on 50 binary classification data sets, and we set the Rashomon parameter to 5%. After we computed performance of our 5 algorithms and we computed the Rashomon ratio, we plotted that performance and we ranked all the data sets with respect to Rashomon ratio from highest to lowest. And what we actually saw was that all data sets with highest Rashomon ratio, as on this slide, they had similar performance, similar train performance, 1, and similar generalization guarantees, 2. It Interestingly, the opposite didn't happen. So if we took, for example, data sets with lowest Rashomon ratios, they could have both properties. They could have similar performance and good generalization guarantees, or the performance could be all over the place. So it actually gives us an interesting understanding that larger Rashomon ratios correlate with similar performance of algorithms of different complexity. This gives us an instructions that we could follow to answer our question. So we can ask a practitioner to run different complexity machine learning algorithms on a data set. Now, if all methods perform similarly, it could mean that the Rashomon set is large. Therefore, one can go and optimize for the simpler interpretable models in order to get them, and that search is actually justified. However, if the algorithms perform differently, it is possible that the Rashomon set is small, and then practitioners should actually consider a more complex hypothesis space. There is another interesting question, which is how often do actually larger Rashomon sets occur in practice? So turns out they occur a lot in real world. And one obvious answer to this question could be that, larger Rashomon sets are when we have good data representation. So let's say we have well-separable data with large margins, then yes, we will have larger Rashomon set. Another case might not be that obvious. It's actually when we have a lot of noise. So Rashomon sets increase with feature and label noise. And to see this, let's consider an illustration where we have data that are generated from two Gaussians, where positive data points come from the red Gaussian and negative data points come from the blue Gaussian. And we have their means, mu1 and mu2, and standard deviation will be 1 in both of these cases. Also, our hypothesis space will be decision stems. Then we will add or remove noise by actually moving these Gaussians towards each other or further away. So as they move closer to each other, we add more noise. As they move further away, we remove noise. We will also measure the Rashomon set. And what we found out and fully numerically verified is that Rashomon set is actually the smallest when these two Gaussians intersect in their ignition point. When we move them closer to each other, the Rashomon set grows as we add more noise. When we move them further apart, the Rashomon set actually also grows as we make the data representation better. So what we just discussed, in fact, explains the phenomena that happens to so many real-world problems in healthcare, medical, financial data sets. We often see that they are very noisy and they have larger Rashomon sets, which justifies actually the search for sparse or interpretable models for them. Okay, to sum up, larger Rashomon sets can embed models from simpler hypothesis spaces, and then these models will have good generalization guarantees. We show that theoretically. Empirically, we observed that larger Rashomon sets correlate with similar performance across different machine learning algorithms of different complexity, so as their test performance. The Rashomon ratio is a measure of learning problem simplicity, and data that approximately arise from overlapping Gaussian distributions tend to have larger Rashomon sets. Thank you for your attention.